Hello everyone, my name is Tim Ballard. I'm from the University of Queensland, and this is a project that I'm working on with Andrew Neal, Simon Farrell, Andrew Heathcote, Aaron Lloyd, and Jonathan Lim. Before I get started, I'll start out by pointing out that I've put a link to the preprint of this paper on the slides, so anyone who wants to read more about the project can access it there. The key construct that we're interested in here is goals. So how do goals affect motivation and decision making? There are, of course, a lot of different types of goals. A day trader, for example, might aim to hit a profit target by the end of the day. A bushfire fighting team might have the goal of slowing the progress of a bushfire to a certain rate. Or we might have more abstract goals like being a better person. Here we're specifically concerned with so-called SMART goals. So these are goals that are specific, they're measurable, meaning that the progress towards the goal can be quantified. The goals are achievable, relevant, and time-bound, meaning that they have a deadline. For our purposes, the measurable and the time-bound properties are going to be the most important because these are the ones that are dynamic. By dynamic, I mean that these properties change over time as one pursues a goal. So you can think about your current state with regard to a goal as a position on this two-dimensional plane. So here the x-axis represents what you might call the distance to the goal. So the distance is how much progress needs to be made before you reach your target. So for example, if I'm hoping to raise $1,000 by the end of the month for charity, and I've currently raised 300, then my distance is 700. The y-axis represents the time to the deadline, so how much time remains before I'm expected to have reached my target. And the combination of these two dimensions determines the difficulty of the goal. So anywhere above the diagonal in that red region, it's a little bit easier to achieve the goal because there's more time and less distance to cover. Below the diagonal in the blue region, the goal is harder to achieve. The question we're interested in here is how does the motivational value of the goal change as you move through this space? There's a great deal of theory that speaks to this question, but the theory tends to be verbal and is generally rather narrow in focus. So for example, there's a whole class of theories that makes predictions about the relationship between distance to goal and motivation, which in this project we've referred to as the distance gradient. But these theories typically ignore the influence of time. Not only that, they disagree on what the nature of this distance gradient is. There's what I've called the proximity perspective, which assumes that motivation increases as you get closer to achieving the goal. So this perspective dates back to the goal gradient hypothesis. But there's also what I've called the discrepancy perspective, which assumes that motivation results from there being a discrepancy between your current and desired state. And as such, motivation decreases as you get closer to the goal. Here we model the distance gradient as a power function so that we can capture the diminishing returns in this relationship. So a positive exponent, the delta parameter here, gives you a positive distance gradient consistent with the discrepancy perspective. A negative delta gives you a negative distance gradient, which is as assumed by the proximity perspective. There's also a group of theories mainly based on models of temporal discounting that address the influence of time. There's more agreement among these theories. The agreement is that motivation increases as the deadline looms. But these theories rarely take into account how much progress needs to be made, so they ignore the distance gradient that we just spoke about. Here we model the time gradient in this way, the same way as we model the distance gradient, except that we don't really expect the exponent to be positive here. So in this analysis that I'm going to present, we're going to constrain the tau parameter to be negative. And then there's a third class of theory that doesn't explicitly focus on distance or time, but addresses the relationship between goal difficulty and motivation. We call this relationship the rate of progress gradient because difficulty in this context is determined by the rate of progress that needs to be sustained in order to achieve the goal. In other words, the ratio of the distance to be completed to the time available. And here there's also a conflict. So what we're calling the expectancy perspective, which is largely based on expected utility models of motivation, assumes that motivation increases with the likelihood of achieving the goal, and therefore reduces with the rate of progress that must be achieved. So the easier the goal, the more motivated people are. There's the difficulty perspective, which assumes that motivation increases with the rate of progress needed, because people, according to this perspective, prefer to pursue more difficult goals. This perspective is consistent with studies of time pressure, which show that people adjust their effort expenditure in line with the rate of progress that's required. And finally, there are theories that propose a non-monotonic relationship between difficulty and motivation, such that motivation is highest when difficulty is at a moderate level and lower when the goal is too easy or too hard. I've called this the achievability perspective because the inflection point here is generally assumed to occur around the point at which the goal transitions from being hard but achievable to being too difficult that it's not achievable. Because of the potential non-monotonicity in this rate of progress gradient, we use a different function here, which via this alpha parameter captures all three of these possible scenarios shown in these graphs. So we've identified 6 theoretical perspectives that address how motivation might change as a function of distance to goal and time to deadline that can all be expressed as special cases of this more general 3-gradient structure. So our model assumes that the motivational value of a goal, which is given by M, is just a weighted sum of these 3 gradients. So we can use this architecture to examine whether any one of these theories is sufficient to account for the dynamics of motivation in its own right, or whether more than one perspective needs to be integrated. In the paper, we apply the model to both experimental and naturalistic data. I presented the experimental data at American Math Psych last year. Here, I'm going to talk about the naturalistic data. We obtained data from 28,000 professional basketball games from the NBA, which is the National Basketball Association in the US. Basketball provides a useful context for making insights about the dynamic motivation because there's a clear deadline at the end of the game, a clear goal, so to have more points than your opponent, goals that are regarded as particularly important. People are highly invested in winning the games, and it also involves different types of goals depending on your current state. So when a team has fewer points than the opponent and they need to catch up, they're pursuing what we call an approach goal because they're trying to move towards a more desirable state. When they have more points than their opponent and they're working to prevent their opponent from catching up, they're engaged in an avoidance goal. The outcome variable of interest, which was our measure of resource allocation or effort expenditure, was the number of seconds per minute played by the team's top 5 players. So in an NBA game, there are 5 players per team on the court at any given time, and teams are allowed an unlimited number of substitutions. So coaches use these substitutions strategically to manage the trade-off between productivity and overworking the team's most valuable players and risking injury. So the higher the workload allocated to the team's top players at a given point in time, the more we can say that a team is invested in attempting to win the game. So we define the top 5 players as the 5 players who start the game, who are known colloquially as the starters. These are typically the strongest players on the team. We used a beta binomial likelihood function to link the model predictions to the data, where the center of the distribution was determined by the motivational value quantity M, predicted by the model. The model included a bias parameter, kappa, to capture the overall tendency to allocate workload to the top 5 players, as well as a noise parameter, theta. And the model was fit using hierarchical Bayes, where the lower level unit of analysis was the games played by one team in 1 year. The top row here shows the number of starters on the court as a function of the score difference, which is given on the y-axis, and the number of minutes remaining in the game, which is given on the x-axis. Red areas represent scenarios where the team invests more heavily in the game. These tend to be situations where the score is close and when there are fewer minutes remaining in the game. Blue areas represent regions where the team is less invested, which happens when they are either winning or losing so much that the outcome of the game is effectively locked in. So the top right-hand corner of each panel and the bottom right-hand corner. We also divide the games by importance here. So the left column shows preseason games, which are unimportant because they don't count towards the team's overall record. As you can see, they invest less in winning those games than in the other games. The middle column is regular season games, and the right column shows so-called playoff games, which are particularly important because a loss here can mean the end of the season for a team. As you can see, these trends tend to get stronger as games get more important. The bottom row shows the posterior predictives of the model. As can be seen, the model is able to reproduce the qualitative trends in the data, although it doesn't quite capture the magnitude of some of the effects. So in particular, its predictions are slightly less extreme in many cases than the data. In order to capture the 6 perspectives I spoke about before, we use the parameter estimates to reconstruct the 3 gradients for each participant. So we could see what that two-dimensional plane actually looks like. So on the left is the prediction implied by each perspective again. It's the same plot that I showed several slides ago. And on the right is what we estimated for each type of goal. So for both types of goals, the first thing you should notice is that the estimated plane looks quite different from the planes predicted by any one of the 6 perspectives. So it turns out teams care about all 3 gradients. In particular, it appears that the proximity perspective with regard to the distance gradient, the time gradient, and the achievability perspective with regard to the rate of progress gradient are all needed to account for the data. In the paper, we show that formally with some model comparisons. You can also break these results down by team and by gradient in order to get a sense of what the individual differences look like. Although there was variation in the magnitude of certain effects, the patterns were quite consistent across teams. So in terms of the distance gradient, every single team had a negative gradient here, which provides evidence for that proximity perspective and evidence against that discrepancy perspective. The time gradient was constrained to be negative, so the direction of the effects shown in the second row is not particularly diagnostic. There was variation between teams, though, in the strength of that effect. And finally, almost all teams had some amount of non-monotonicity in the rate gradient. So as can be seen by the bottom row there, the shape of the rate gradient was quite similar across teams, and it had an inflection point that was at a fairly moderate level of difficulty. You can also use this model to answer the question of how more precisely does goal importance affect the dynamics of motivation by examining the pattern of gradients across the different types of games. There were 2 key differences that emerged here. One was that teams were more sensitive to their current state when playing in more important games. So although there weren't clear differences in the relative influence of the gradients across the different game types, those gradients in general were more influential in more important games. So in other words, teams were more responsive overall to their environmental state. The second key insight here was that teams demonstrated a higher overall tendency to allocate workload to the top players. So regardless of their current environmental state, there was a quote-unquote bias, you could say, so toward investing more in the game, which is not particularly surprising. So the main conclusion here is that none of the 6 perspectives outlined at the start of the talk is sufficient to account for the motivational dynamics by itself. These dynamics are complex, and so we need theoretical integration in order to more fully understand how they work. We found that all 3 gradients were relevant, and that we need to draw on at least 3 perspectives in order to understand these dynamics. We need to draw on the proximity perspective, the time perspective, and the achievability perspective to account for the dynamics at play in this context. And these results were remarkably similar across teams. In terms of future work, we want to be able to use this model as a front end for example, models of speeded choice. So right now we're working on a project where we integrate this architecture with the LBA to explain how people regulate their response caution over a sequence of decisions trying to achieve a goal within a certain amount of time. That's all for me. Thanks for taking an interest in the project. I put my contact details there for anyone who's interested. Feel free to get in touch with any feedback. There's some references. Other than that, all the best.